In this paper, we introduce an accurate neural implicit representation for diverse 3D shapes, named unsigned orthogonal distance fields. Compared with the common implicit shape representation SDF or UDF, the most distinguishable feature of UODFs is that every point in 3D UODFs can directly access its nearest surface points along three orthogonal directions if intersections exist. The proposed UODFs consist of three orthogonal distance fields, each of which can be considered as a set of all 1D UODF of parallel rays in the same orthogonal direction. Along one orthogonal ray, UODF of each point defines the distance to its closest surface point, which is the nearest intersection of the ray and the shape. Take one ray in the front-back direction, for instance. The ray has 9 equally spaced sample points, drawn in green. It intersects the bunny at two surface points. On the upper right, through position encoding of 2D coordinates of 1 point, we obtain the ray feature used to train the mask network. Concatenated with its 3D coordinates, we obtain the point feature used to train the UODF network. The 1D UODF of this ray is drawn on the lower right. It can be seen the UODF values of 9 sampling points and 2 intersection points. In inference, each sampling point individually predicts its nearest surface point according to its UODF value. The intersection point on this ray drawn in yellow is estimated by averaging all predictions of sampling points on a ray segment in an interpolation-free manner. In addition to the aforementioned method of smoothly estimating each surface point from multiple sample points, UODFs also facilitate single-point estimation for surface point reconstruction. We design a midpoint-based searching algorithm to iteratively identify the hit points intersected by each ray and the model. This slide presents a slice of 2D UODF in each orthogonal direction for the Dragon model. Unlike SDF or UDF, UODF may exhibit the discontinuity between adjacent rays. This behavior is similar to planar laser and facilitates the direct and accurate prediction. It can be seen that our prediction for the discontinuous UODF is accurate, without obvious errors. Detailed configurations of UODFs are listed below. We would like to emphasize that all our reconstruction results presented next are free of fine-tuning the network and hyperparameters. First, we show the reconstruction results of single-layer watertight shapes. The baselines are Siren and GLOD with level of detail 3 and 5. Our UODFs can reconstruct these watertight shapes with high quality. Second, we show the reconstruction results of non-watertight shapes. The baselines are NDF, GIFs, and HSDF. Our UODFs outperforms the others significantly for reconstruction of the non-watertight shapes. Third, we show the reconstruction results of complex shapes. The first two shapes are a birdcage and a gear. Both of them are watertight but have many hollow structures. Next are two assembling shapes. The first one consists of the inner bunny and the outer hemispheres, and the second one consists of the inner multilayer fish and the outer hollow but watertight box. For complex shapes, our UODFs can still reconstruct them with high fidelity. Fourth, we show the reconstruction results obtained from the implementation of triplane encoding and single-point-based GEP estimation. The metrics from left to right below each mesh model are GEP estimation time, chamfer distance of mesh, and normal consistency of mesh. By utilizing the single-point-based GEP estimation method and triplane encoding, the GEP estimation speed is accelerated by nearly 2 orders of magnitude without degrading reconstruction accuracy. Fifth, we show the reconstruction results using 3 mesh extraction methods, DSE, DMNet, and masked SPSR. The metrics below each reconstructed shape, from left to right, are chamfer distance of mesh and normal consistency of mesh. At last, we show the reconstruction results at multi-resolution grids. For the watertight CAD and the non-watertight clothes, We compare to marching cube and mesh UDF using ground truth SDF and UDF as input, respectively. Our UODFs can reconstruct the high-quality shapes at various grid resolutions. Except the above-shown meshes, the reconstruction results of grid edge points GP are also visualized. The reconstructed GEP are drawn by small green spheres, along with the ground truth mesh, drawn in red. It can be seen that our UODFs facilitates GP reconstruction, especially at lower resolutions. Thanks for watching. Please refer to our manuscript for more details and results.